there, that is Marconi, as some hecklers have already suggested. And basically, this is based on a trip that my wife and I took to the Maritime Provinces this summer. And we're going to talk a little bit, kind of a chronology of communication across the Atlantic before radio, and the first transatlantic communication, the transatlantic telegraph cables, followed by Marconi and the development of practical radio. Key difference there is practical. Before that time, they had, developed, oh, look at this, I can send signals, but nobody said, what are we going to use it for? And then the application of radio, the Titanic disaster, and what happened after that. So if you're ever in Halifax, Nova Scotia, be sure to visit the Maritime Museum of the Atlantic. This is the station, VA1MMA, and as soon as the gentleman found out that I was a ham radio operator, I was drug into the room and we had a really, really great conversation. This is a super museum, has lots of exhibits, ship models. It talks about the Titanic disaster and also the Halifax explosion, which is not part of this presentation, but that was a very calamitous event in 1917. So, Maritime Provinces are the three provinces shown there: New Brunswick, Prince Edward Island, and Nova Scotia. Oops, wrong button. All right, gotta get the button. Halifax is the main city in Nova Scotia. About half the population of Nova Scotia lives around Halifax, and the total Nova Scotia population is about 1 million people, a little over, and it's about 1/5 the size of Colorado, about 20,000 square miles. And the part to visit is right here, the Cape Breton Island, which has the Cape Breton Highlands National Park, which is really, really pretty. And right on the tip right there is an old radio station that we'll be talking about here in a few moments. And until 1867, Canada was a series of royal provinces governed by the Parliament in London. If that sounds familiar, it's the same as those 13 rebellious colonies that were a little bit farther to the south. Now, they didn't rebel, but in 1867, they developed the Dominion of Canada, which was, whoops, I keep hitting the wrong button, I'm sorry. There we go. Which was Ontario, Quebec, New Brunswick, and Nova Scotia. And eventually the other territories, as Canada became more populated, became the entire Dominion of Canada, with the last one, Newfoundland, joining in 1949. And there is, right off the map, you can't see it, it's kind of southeast of there a little bit, are a little series of islands. And they have call sign FP0, it's St. Pierre and I think it's Miquelon, and that is French overseas territory. So the French still have territory in North America. Okay. So how do you get a message to Europe? Before 1818, you put it on a ship, and the ship might arrive. It might take 3 weeks, it might take 3 months, it might never arrive if the ship sinks. So in 1818, they started what they called packet ships, which would leave at a certain time, whether or not they were fully loaded with cargo and passengers and everything else, but it made it more predictable. Not faster, just more predictable. 1865, we had the first permanent undersea telegraph cable, which obviously, now we're going from days, weeks, months, down to literally hours. And then the 1900s, as we'll see, Marconi and several other inventors made radio a practical alternative. So the transatlantic telegraph cables, that's kind of the triumph and tragedy. It took them 3 attempts in 1857 and 1858 before the first cable was completed. It kept breaking, falling to the bottom of the ocean, start over again. First message was sent on August 16th, 1858, and it worked fine for a couple of weeks. And it started deteriorating. They kept raising the voltage, and after 3 weeks, poof, it was done. And they had sent 732 messages. And the average speed that I calculated was 1.4 words per minute. They had a terrific distortion on that cable because of all the distributed inductance and capacitance from just dropping a wire, one wire, by the way, ground return across the Atlantic. Now, here again, that was from Newfoundland to Ireland. So you then had to have other relay links from Ireland to England, and then from Newfoundland to Nova Scotia, back to continental Canada. Second cable, 2 attempts are required, so they're getting better, only 2 attempts. And they used the steamship Great Eastern. At that time, that was the largest ship in the world. And here again, 1866, this ship is 700 feet long, 33,000 tons. Huge for that day and age. And of course, it had a massive amount of capacity to put, several thousand miles of cable in its holds. And they took there, got it, the cable connected, and they even salvaged one of the other cables that was, run partway across and lost. So they ended up actually having 2 cables working. And after that, just numerous other overseas cables were laid. And today, there's like 600,000 miles of undersea cable around the world, obviously mostly fiber optic now. So in the late 1800s, a lot of people were looking at what is all this, electrical stuff that we're seeing. James Clerk Maxwell predicted that electric and magnetic fields could travel as a wave. It wasn't a physical, signal. It was just a wave front. I found a little graphic there of your electrical and magnetic waves at 90 degrees opposition. And Heinrich Hertz in 1888 actually demonstrated production and detection of electromagnetic waves, which they then called Hertzian waves. And Hertz said, well, this is very interesting, but I don't see any practical application for this phenomena. So I think that kind of happens when you first develop something. Nobody knows what to do with it. And Edward Branly, a Frenchman, in 1880 developed what he called a coherer detector. We'll talk about that a little bit more later. That was the first primitive detector of electromagnetic signals. And you have to remember, there are no electronics at this time. This is a completely mechanical system. And that's what kind of really intrigued me, is how the heck do you send radio signals without any electronic equipment? And this is your basic spark gap transmitter, circa 1896. What you have is a battery, power source, DC, a key, basically a step-up transformer, kind of with a solenoid, with this little connection here, that it will open the connection when you put the key down. You get your spark gap to actually make the signal, and then you, this shows one with a kind of a crude tuning device, the coil, and a capacitor, making somewhat of a tuning situation. The way this works is you put the key down, the flux starts to build, and then this opens, breaking the circuit, field starts collapsing, generating the spark. Well, the moment it collapses, then this makes contact again, which starts it rising again. So it's just doing this 20 to 1,000 times a second. So you can actually hear this. Another kind of a viewpoint of the system, a little more graphical or picture. They're little dry cell batteries, telegraph key. There's your induction coil. And this little thing right here is a little, that little contact that keeps buzzing like that to a spark gap. And back in the 1890s, capacitors were Leyden jars. This is basically a liquid capacitor. That looks like a hassock, but that is their tuning coil going up to the antenna, and of course you have it grounded. So this transmitter is a damped wave oscillator, which means you hit the spark, it's one spark. If you want to send the signal, it has to just keep sparking all the time. Okay, it's not a continuous wave like CW is. And the original radios didn't even have the tuning coil and the Leyden jars, which we'll be able to see here. Is this, uh-oh. Hang on. There we go. We have a little short video here for you.
Okay, this is the simplest radio transmitter that you can make. So here I have a battery, and it's connected to these two paper clips, and these act as a switch because you push it down, they make a connection. And it goes up here to this coil of wire. That's all it is. Well, it's coil of wire. It's got some nails in there too. And then this is a steel plate, a bendable steel plate, and it's connected back to this nail that's touching that, and that's the end. And then that goes back to the battery. So when I push this, it runs a current through here. It turns on the electromagnet, which pulls this, which disconnects the current, and then so it repeats all over again. So let's run it.
And your spark is being developed right in there.
Okay, and it does this changing current makes a voltage, and the faster you change the current, the greater the voltage, and that creates a spark. Okay, so now how's this for radio transmitter? So here's my radio. I'm going to turn it on, put it on AM. That's making radio waves detected by the radio.
Isn't that a lovely signal? And you'll notice he did not tune the radio anywhere because this is a super broadband signal. Next slide. Okay, now you have a transmitter, you need a receiver. The receiver was the coherer detector, and that was a very, very primitive unit. It consisted of a glass tube or capsule with two closely spaced electrodes. That's this unit right in here, okay? And it had loose metal filings in between. And what happened is when you hit an electromagnetic field, or it sensed it, the filings would cohere, which they still kind of don't understand that mechanical electrical process. But anyway, the resistance across the coherer would decrease dramatically, okay? So it's like basically a switch. So it's either open or closed, open, closed. And what they did is they would then attach that to a different circuit that had like a moving arm, like with the solenoid on it, so that when it closed, it would cause it to move up and down, and they'd record that on paper tape. So it would be literally like, you know, if you will, zeros and ones, kind of you'd see on a digital signal, but it was, you know, a long would be a dash, and, you know, a short would be a dit, okay? Now, the one problem with the coherer is that it wouldn't decohere. So you had to physically tap it all the time, and that's what this little device in here is. So it's going all the time, many times a second, to decohere and then recohere, decohere. Incredible mechanical device. And then by 1907 or so, they were using electrolytic and the old cat whisker crystal detector. That was very popular in many crystal radios in the early 1900s. Now, coherers had one problem. They are voltage threshold detectors. They'll detect anything, okay, any electromagnetic field. So Robert Marriott, first president of the IRE, which became the IEEE, said the device was publicized as wonderful, and it was wonderfully erratic and bad. Would not work when it should, and it worked overtime when it should not have. And Mr. Greenleaf Whittier Packard, a researcher and another president of the IRE, says, all was fish that came to the coherer's net. So you can get the idea from, you know, a fisherman. He's got a net out there, he catches everything. The recorder wrote down dot and dash combinations quite impartially for legitimate signals, static disturbances, a slipping trolley several blocks away, and even the turning on and off of lights in the building. Translation of the tape frequently required a brilliant imagination. Needless to say, it was not the best in the world. And they were also incredibly deaf. This is a very poor detector. And we'll talk a little bit later that to make these things work, they needed transmitters that were massively powerful because the detection systems were so poor. So the main hero of our presentation here is Mr. Guglielmo Marconi. And he was born in 1874 into a wealthy Italian nobility. His mother was Irish, a Jameson. You've heard of Jameson and Sons Distillery? Yep, same Jameson. And so since they were wealthy, he got homeschooled by tutors, and he was evidently a brilliant child because when he was 18, he started studying with a Professor Augusto Righi at Bologna University. And the professor was very much interested in the electromagnetic theory, had done a lot of work with Maxwell's equations and Hertz's demonstrations. So Marconi decided, well, let me see what I can do myself. So in 1895, when he was 21, he starts experiments at home using the coherer that we just talked about. And he discovered that a higher antenna and a grounded system improved his results. So, you know, we're talking basic days of radio. And if we look right here, this looks to be his battery box on the floor, going up to his telegraph key. This is the induction coil. And you can see this deal right here is probably the little tapper, you know, that pulses the induction coil. That's his spark. And this, what looks like a sheet of aluminum foil, is his antenna. So that basically is Marconi's first radio. And he just kept improving it over time. And people thought it was a great, fantastic demonstration, but there really wasn't any interest in it in Italy that he could find. So he goes to England and talks to some people there. I think his mother probably had some contacts there that they work with. And so he got a patent for transmitting electrical impulses and signals, the first patent for a radio system. So in 1899, he goes to the United States and was wildly acclaimed as, you know, this is a great scientific development. Now Marconi, being a smart guy, decided, oh, I'll make some money off of this. So he said, well, we're going to bridge the Atlantic with this thing. And I can charge people for sending messages. So, and we'll go into details a little bit later, but the first signal was received by Marconi across the Atlantic in 1901, maybe. And we'll talk about that in a moment. In 1902, first confirmed one-way message, and then in 1903, first transatlantic two-way message. Remember, no electronics whatsoever, just mechanical devices. And you see how poor the coherer detector is. This picture is of some British post office engineers. And as an engineer, I never had to wear a hat like that, thank goodness. But here again is your induction coil. These are probably the spark gaps. And what you can see down here, what this looks like is this gentleman is pulling a paper tape. So I'm thinking that's the paper tape recorder. As I said, when the coherer received the message, it would make a circuit that would cause, you know, on, off, that powered a little lever to just move against a piece of paper. And that's what's scribed. And then you have to kind of interpret what the scribbles meant. So this is a map that was on a wall in a museum. It's the only one I could find that actually had where the paths were. So Marconi said, to span the Atlantic, I need a powerful station. So he built a station at Poldhu in Cornwall, England, right here on the southwestern tip of England. And then he built a receiving station on Signal Hill in Newfoundland. And it was called Signal Hill because it was where a cable company, undersea cable company, had one of their terminations. And we'll be talking a little bit about this path, which is the tip of Nova Scotia, where he built another station. So you just get an idea of the path that they're trying to traverse. The Poldhu station in Cornwall was a monster for its time. It had a different type of antenna system. It was just round wires coming up, but it got destroyed. So you had to make a temporary system, which was just a two-mast design. Built the receiving station at Signal Hill in Newfoundland. As we said, it's about 2,200 miles. Estimated power at Poldhu was 10 to 12 kilowatts. And the frequency, they weren't measuring frequency. They had no idea what frequency was. They were measuring meters, if anything, and they probably weren't even measuring that. So it's somewhere between 166 and 984. And I don't even know where the numbers came from, but that's what they guessed it was. Now, after his 1901 test, which he may or may not have heard the signal, they rebuilt it to the kind of Marconi standard transmitting system. Okay, you got a powerhouse, coal-fired generators powering electric generators, massive spark gaps in here, and 400 wires going up to 215 foot tall, 200 foot square antennas. Now, if somebody would like to go use the antenna modeling program and tell me what kind of propagation pattern that has, I would be happy to, add that to the presentation. I have no idea what this was. And of course, since they were, I don't know if it matters, because since he was using literally all frequencies anyway, I guess it projected somewhere at some frequency. Guys, we're really, this is very unscientific at this point. So, his receiving station at Signal Hill, St. John's, Newfoundland, was a single wire, 500 feet tall, held up by a kite. So I'm assuming that Signal Hill has a lot of good winds on it to keep that kite up for hours at a time. And these are some of the guys helping with it. Okay. So here's the deal. Marconi claimed that he heard the letter S several times on December 12, 1901. They said, wow, this is a great achievement. Well, there's a lot of skepticism on that. The concerns are, first of all, it was around, in that broadcast band, which is today's AM broadcast band, which, we don't really use for DX a whole lot. Very low frequency. Secondly, midday, the D-layer absorption, it's not going to bounce anywhere, okay? Plus, the kind of a confirmation bias problem, he was expecting a signal S. First of all, that's a very simple signal, why not something hard like Q or L or something like that? But he said he heard it. Well, it looks like very, very skeptical that he actually heard that signal at all. So he said, okay, I'll show you guys. So he did a better test. He got on the SS Philadelphia. He probably chartered it since he was rich. And he sailed from pole to west. And every day he kept recording signals from the pole 2 station. And he got coherer tape reception, the paper tape, up to 1,550 miles. And it said, the article I read, it said audio reception up to 2,100. And I'm not sure what the audio reception was unless it like rang a bell or something. The article didn't give me much information what it was. But anyway, he's hearing it, practically the entire distance across the Atlantic. So he says, I know this will work. So the first thing he did is he got rid of the coherer detector. He said, I need something better. So he developed a magnetic detector that used a rotating iron belt. And you can see these two spindles right here, these two round things, I guess. And you can kind of see that it looks like there's a little wire that rotates along here. I'm assuming these U things are the magnets, and that is probably some kind of a pickup device in there. And so that allowed him not to have those decoherer tappers banging away all the time. So this he was able, and it's much more sensitive. And this was standard Marconi equipment until about 1912, when we're finally getting all the crystal detectors, and even Fleming and the other guy, I forget his name, that developed, the first actual vacuum tube, the vacuum tube diodes. DeForest, thank you. DeForest and Fleming. And so the next thing is the cable company said, oh, I think he's going to be competition for us. Get rid of your station. So he was kicked out of the Signal Hill station, and he went to the Canadian government and got a grant of $80,000, about $3 million in today's money from the Canadian government. And the stipulation was build your station on Canadian territory. Well, of course, Newfoundland was not part of Canada at that point in time. So he had to move from Signal Hill, and he's studied a lot of places in Cape Breton area and picked Glace Bay, Nova Scotia as his new location for a station. And this is a picture from 1902. You can see here again, standard Marconi design, 4 towers. I'm not sure what these other structures were. They might have been something else he was doing, not sure. And you can see it's right on the cliffs. That's the Atlantic Ocean. Not much of a better site than right there. So he had all of his good propagation characteristics that we would love to have. And these are wooden towers. So you can see these little bitty dots up here, in here, and here are the guys working on the towers. And as we saw in that other drawing earlier, 400 wires in that square conical shape of some kind of propagation pattern. Who knows what? Okay, and so December 17th, he made the first one-way confirmed radio message. So it was a full message this time, and he didn't know what he was going to get for sure. So, they received a message, and then they would run over to the telegraph cable office, send a message saying, this is what I received, and then they'd go back and forth, so he was still having to use the cable to confirm that he had received the message correctly. Their first official two-way message was the official greetings between President Roosevelt and King Edward VII, saying, congratulate, this is a message from the radio. Oh, thank you very much. All the official hoo-ha. And Marconi started regular transatlantic radio telegraph service on October 17th from Clifton, Ireland to Glace Bay, and he won the Nobel Peace Prize in 1909. However, he had to share it with his bitter rival, Mr. Karl Braun of Telefunken Company in Germany. And reading the histories, there were other people that were claiming they developed radio also. There's a gentleman, Popov, Russian, who in the same late 1890s claimed he had developed radio also. Point is, who made it actually work? Marconi is the one that put the effort in to actually make it a workable, practical system. And he died in Rome in 1937 after his 9th heart attack. He must have been a tough dude to make it through 9 of them. And this is a picture of their house in Bologna, Italy, and this is his tomb right there on the estates of the ground. So he was, like I said, he was the guy that made radio work. So they have, Parks Canada has the Marconi National Historic Site there at Glace Bay. And you notice, of course, the dual language. In Nova Scotia, it was not an official dual language province, I'd say. It was probably 90–95% English spoken, but we heard a fair amount of French-speaking people up there. Very nice trip. If you ever want to go to the Maritimes, there's a lot of other things, but they're just not enough time to put it in the presentation. And you'll notice there's a this modern wireless radio antenna sitting over here, just to the side of the building. That's the museum. And the museum has a lot of exhibits about Marconi, and they've got a couple foundations from those original towers left, but that's all that's left of the original station. And of course, you got to have the ham station. That's Al, who will talk your ear off, VE1ALZ. And as soon as he found out I was a ham radio operator, I got the premium treatment. And he had lots of good information. He dedicated QRP-CW operator. And the equipment is provided by Parks Canada, so there's no opportunity for guest privileges. So that was kind of a bummer. But still, I had a great time visiting with Al and getting a lot of the other detail that, you could go a little more technical than the average visitor. And this is a model that's in the middle of the museum of the 1902 station. So here's the powerhouse with the big coal-fired generators, or coal-fired, steam, that generated steam that ran the actually electrical generators, DC generators. There's your 4 towers with the 400 wires going up to the, for your antenna. Oops, hang on. Okay, yeah, it said coal-fired boilers provided the steam, and the generators provide about 75 kilowatts of power. Not sure how much of that ended up actually going up into the antenna. I'm not sure people really, I don't think they were able to measure a lot of the stuff at that point in time probably. And the spark gap, it did use a simple tuning circuit. Like I said, I showed the Leyden jars. I think they're actually using, I've seen some pictures, they weren't high quality pictures, so I didn't include them, about the, they're like massive, huge sheets of lead or something. So they weren't compact like the ones we have now. And so there was some tuning available, so it kind of reduced that massively wideband signal a little bit. Now, and I looked at this and I found out this is apparently the only surviving picture of the actual Titanic radio room. And you can see there's a lot of reflections, like a double exposure on a lot of this, so it's not the best picture. But this is the picture of the back of the head of Harold Bride, one of the operators. Because the gentleman, photographer, had got on in England, and the Titanic actually went from, let's see, where did it go? It went from England down to Cherbourg, France, and then another stop either in Ireland or Scotland before it went across. And this gentleman took pictures and then he got off the Titanic. So that we have some pictures still existing of it. So, and here again, Marconi, being the businessman, decided that he'd like to make money. And so in addition to that transatlantic service, by putting it on board ships, he could charge for messages and give a little bit of a royalty also to the White Star Line. So this was becoming somewhat more common in 1912 when the Titanic was launched and went for its first voyage. But like I said, the equipment and the operators were Marconi employees. And as far as, that looks like some keys, that looks like the induction coil. I'm not sure what some of these other items are. Like I said, it's not the best photograph in the world, but it actually is of the Titanic. Okay, that's another YouTube. So we're going to bring up another video here. This is an actual Marconi standard, if you will, piece of equipment. So this is like the Marconi Model 1 transmitter. And so this is from the Canadian National Science Museum or something like that. So go ahead, Dave.
Spark gap transmitter from the early days of radio. And the way this worked essentially is that it's a big step-up transformer, and the telegraph key is a switch that turned it on and off. So when you close the contact with the telegraph key, a spark jumps across the gap between these two electrodes over here, like this. And this would also be hooked up to an antenna, so that would be spewing out radio waves across a broad spectrum of the radio frequency. The problem with these is that when one was going, the sort of strongest, loudest one was the one that could be heard, and you had trouble hearing all the rest of them. And this actually came up on the Titanic because the radio officer on the Titanic was broadcasting messages from the passengers of the Titanic, which was a money-making operation for the Titanic and the Marconi company. And the Californian, a ship nearby, was stuck in the ice field and was trying to broadcast a warning about that. The Titanic radio officer asked him basically to shut up because he was trying to hear his relay station that was helping him broadcast his passenger messages. So the Californian radio operator complied, shut up, turned his radio off, and I guess the rest is Titanic history. So we'll just show you the spark again. A little technical detail about this. This is an important part of this equipment as well, too.
Notice
this is
the
the make and break hammer contact here. It works like a doorbell, essentially. So when I turn the power on to the coil here, it creates a magnetic field which pulls this contact over this way and cuts off the power. So then that comes off back this way, turns the power on again, and it goes back and forth like that. So that pulsating magnetic field is what allows this to operate as a transformer on a DC source.
That was the interesting part about that is, that's how you get a RF signal out of just a DC source. Like I said, no electronics. To me, that was just totally fascinating. Ready? Okay. So I'm sure you've all heard the story of the Titanic. Contributing causes: excessive speed from pressure to, meet schedules, be the fastest, win the blue ribbon prize for the fastest liner. No binoculars for the lookouts because the binoculars were locked in a locker, and one officer had a key, and he left the ship and kept the keys. So they didn't have any binoculars, so they're out trying to look for icebergs without any binoculars. And lack of best use of radio technology, kind of not their fault. This was so early, but they weren't used to talking to other ships. These were strictly commercial message services, basically. And there's some theories about the steel became very brittle in the cold Arctic waters that they didn't realize when they made the ship. It may have caused additional damage. I've heard one report that says, if they hadn't seen the stupid iceberg and had rammed it bow on, it probably wouldn't have sunk, because it would only probably have got water into one watertight compartment, and they could have survived that. What it did is it flooded, I think, like 4 of the 7, and they said, nah, we're going down. So, aftermath of the Titanic. Oh, wait a minute. We have the SOS signal from the Titanic, sort of. Now, UCW guys, it's pretty fast, so get ready to copy. Uh-oh. CQD was the standard signal from the Marconi system, and they're an international system. It just developed SOS as a disaster message. And the one operator told the other one, says, well, you better use the new SOS because this may be your only chance to use it. And of the 2 operators, one survived and one did not. So they had a very good first-hand account of what happened, and they stayed basically until the water was flooding the radio room. So that made those guys heroes. So, aftermath of the disaster, 1,517 people, give or take, they don't have an exact count, died, but 706 were saved due to radio. The Carpathia took survivors to New York City, and I guess a few bodies that they were able to get out of the lifeboats and everything else. Dead bodies that were still afloat, and I didn't know this before I went to Nova Scotia. Ships from Halifax went out and collected the dead bodies that they could find that were floating, because they'd put their life jackets on. So they took them back to Halifax, and those that could not be identified were buried in 3 different cemeteries in Halifax. So there are some people from the Titanic buried there in Halifax. After the disaster, they set up an international mandatory 24-hour radio watch on passenger liners, which most of them, probably had radio at that point, but they didn't have a 24-hour watch. More lifeboats were required because up to that point they're saying, we just need lifeboats to transfer to another ship that will save us. They didn't consider the fact that they might just sink in the middle of the ocean. International Ice Patrol was established, which the United States Navy and Coast Guard were actively involved in. It may or may not still be going on, I'm not sure, with all our other technology we have. And the biggest important one for us, of course, is the Radio Act of 1912 was passed by Congress. There was a lot of chaos on the bands that night. I guess maybe kind of sounds like 80 meters does today. There was interference to the other stations, the Titanic station, the Carpathia, and some of the other shore-based stations, because the Titanic was only a couple hundred miles outside of Nova Scotia, Halifax area. So President Taft called for changes resulting in the Radio Act. Number one, all stations would now be licensed. Okay, you had to have a license. You didn't have to before 1912. And there are various types of spark gap transmitters. Some were noisier than others. I won't go into the details, but they basically said the noisy type were out, and then by 1934, all spark gap was out. So you can't really make a spark gap transmitter anymore legally. And amateurs were limited to the frequencies under 200 meters, because we all know that anything above 1.5 megahertz is just worthless for communication. I mean, I don't know how we lucked out, but at that point they said, oh, we'll just give them all that other stuff that's not usable. And we were limited to 1,000 watts output. Well, that was, low power. That was QRP in spark gap days. But, obviously as our technology improved, that gave us some nice, decent, powerful radio systems. And acknowledgments. Thanks to Marconi National Historic Site. And there's a couple of books here, not necessarily directly related, but I found interesting. I'm kind of a history fan. Story of the Atlantic Telegraph is talking about the undersea cables and all the trials and tribulations they went to. Mentioned earlier, there was an explosion in Halifax Harbor. In 1917, a ammunition ship collided with another ship and blew up and killed 2,000 people and wounded about 1,000. Pretty much destroyed most of Halifax Harbor and Dartmouth on the other side of the bay. And Longitude is a story about a gentleman, a non-professional gentleman, I think he was a carpenter, that developed a method to determine longitude at sea. Up to that point in time, the sun gave you your determination of latitude, north-south, but they didn't know where they were east-west, which caused numerous shipwrecks, of course. But the key was making a precise clock. It's quite a fascinating story, so anybody's interested in those. And of course, Wikipedia. Where would we be without Wikipedia? Articles about Marconi, coherers, spark gaps, a lot of that I used to distill down to the presentation. The 3 videos we had, Rhett Elaine, I guess that is, he does a lot of science type demonstrations. You find those interesting. And then the Marconi induction coil spark that we saw from the Canada Science and Technology Museum. And if you caught it in the credits, AF2Z for that RMS Titanic SOS. And last but not least, I didn't do the slide presentation. I just gave the data to my daughter, and she has done this professionally for 20 plus years. So she did that for me, and so that partial payback for all the stuff that I've done for her for free. And at this point, have any questions, comments, anything else? That's the end of my presentation. Joe, start with you.
Just a quick question. You mentioned something about using something in a jar for a capacitor. What was it?
I think it was lead sheets and some kind of electrolyte.
Oh, okay.
It wasn't like a battery, but it was a capacitor and I'm not sure of the exact thing. You'd probably have to Google it. But that was the earliest capacitor. Was kind of a liquid solution. So
interesting.
Anything else? All righty, well, thank you.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. For more information, visit our website, ncarc.net. Thanks for watching, and don't forget to like and subscribe.